One of the nice things about linear equations that hopefully you've started to pick up on now is that we can always solve one of them for the variable. Now, sometimes that solution ends up being a number, sometimes it ends up being all real numbers, and sometimes it ends up being that the equation has no solution. But it's always possible to manipulate a linear equation like the one on the screen here so that we have either the variable equals a number or we've eliminated the variable entirely. Now, there are other equations that at first glance might not be linear. For example, this equation. Clearly not linear. There's a variable in the denominator, and that immediately disqualifies it as being a linear equation. However, with some equations, we can do a little creative manipulation and turn them into a linear equation. And from there, we can take advantage of that kind of property of linear equations, that they're where we can always solve them for a variable and get the solution. So let's see how we can do that here. If I take both sides of this equation and multiply it by x, look at what happens. On the right-hand side here, the x's cancel, and this is just 4. And on the right-hand side, I can distribute the x into the parentheses. When I multiply x times 3 over x, the x's are going to cancel, and I'll be left with 3. And when I multiply x times 2, that's just 2x. And now look at what's happened. Now I've taken that clearly nonlinear equation, and I've transformed it into a linear one. So now I can solve this just using our techniques for solving linear equations. I can subtract 3 from both sides, and that gives me 2x equals 1. And then I can divide both sides by 2, and I get x equals 1/2. So there's the solution to our original nonlinear equation. And I need to emphasize, when you're working with these equations, you need to be careful. You always need to go back, and even if you don't completely check your work, which you should be doing, I mean, you should take 1/2 and substitute it back into the original equation and make sure it really is a solution. At the very least, you need to take your solution and make sure it's not going to cause problems in the original equation. For example, and we'll see this in a later problem, you might have a situation where you have a number that you think is a solution, but when you look back at the original equation, it actually makes the denominator 0. So it turns out that really isn't going to be a solution to the problem. In this case, there's no problem substituting 1/2 here in either denominator. So 1/2 is going to be this equation's solution. So let's look at another example. I'm going to kind of do the same thing. I'm going to start just doing some obvious manipulations and see what happens. The first thing I'm going to do, for example, I'm going to get rid of these parentheses by distributing the x into it. And that's going to give me x squared minus 4x equals x squared plus 3. And now look at what happened. I have this x squared on both sides. So if I subtract x squared from both sides of the equation, those are going to cancel, and I'm left with minus 4x equals 3. And if I divide both sides by 4, I get x equals negative 3/4. That's the solution. And you can see, I mean, if you go back and substitute that into the original equation, you'll see we don't have any problems here. That's not going to make any denominators 0 or anything crazy like that. So that is a valid solution. Now, hopefully at this point, you're starting to kind of see what the process is here. Well, what I'm doing is I'm taking the original equation and I'm trying to manipulate it in some way that lets me eliminate the nonlinear parts. On this one, for example, I was able to cancel out the x squareds that were making it nonlinear. On the previous equation, with the rational expressions, I multiplied by something that eliminated all the variables from the denominators. And that's what converted it into a linear equation. So let's look at a few more examples here and kind of see some more examples of how this works. Now, in this equation, you notice that I have a rational expression equal to a rational expression. So with something like this, even if we weren't doing this nonlinear to linear business, my approach to this would still be to try to solve this by cross multiplying. So I'm going to multiply this way, and I will get 2x plus 1 times x minus 1. And I'm going to multiply this way and get x times 2x minus 3. So now I'll multiply these out, and over here I get 2x squared plus x minus 2x minus 1. And on the right-hand side, I get 2x squared minus 3x. And now look at what happened. I have a 2x squared over here and a 2x squared over here. And those x squareds, which were the terms that were making this nonlinear, have gone away. So now I have minus x minus 1 equals minus 3x. And I'll add 3x to both sides. That makes this 2x minus 1 equals 0. And then I'll add 1 to both sides. 2x equals 1. And divide both sides by 2. X equals 1/2. And now remember, we need to double check here. If I put 1/2 into this denominator, it becomes minus 1/2. And if I put 1/2 into this denominator, it becomes 1 minus 3. That's minus 2. Neither of them became 0. So the original equation, both expressions are defined for 1/2. So that's going to be our solution to this equation. So here we have another example. And you might be tempted to do this by cross multiplying, like we did on the previous problem. And you could do that. It would work. But when I look at this, the first thing I notice is that the denominators are the same. So I'm going to approach this a little differently. Suppose we start with, this is just the original equation. I'm just writing it over again. What I'm going to do is I'm going to multiply both sides by x minus 1. So watch what happens here. Now these x minus 1's cancel, and I'm left with 2x minus 1 on the left. And these x minus 1's cancel, and I'm left with x on the right. So now once again we're down to a linear equation. And if I subtract x from both sides, I get x minus 1 equals 0, or x equals 1. Okay, so now if I take this solution and I stick it back up here into the original equation, look at what happens. Let's just look at the right-hand side. This right-hand side becomes 1 over 1 minus 1, which is 1 over 0. And that's not okay, right? We can never divide by 0. So this is an example of the kind of problem I was talking about earlier, where it's essential that you check your solution. Because in this case, when we multiply both sides by x minus 1 here and eliminated this x minus 1 from the denominator, it kind of hid the fact that the two original expressions aren't defined at x equals 1. So because when we substituted our solution back into the original equation, it didn't work, this is in fact not a solution, which means that there are no solutions to this equation. All right, so let's look at another one here. This one is actually going to be very similar, although it looks a little messier. The first thing you need to do whenever you have an equation like this that has a polynomial in the denominator, the first thing I want to do is factor. So if I do that, this becomes 2 over x plus 5 minus 1 over x plus 5, x minus 5 equals still 3 over x minus 5. All right, so now I'm going to start doing some multiplying, just like we did on the previous problems. I want to try to get rid of the denominators And I'm kind of crossing my fingers, hoping that when I do that, I don't introduce any, x squared terms or whatever, and I end up with something linear. So I'm going to start by multiplying both sides by x minus 5. And that's going to eliminate this denominator over here on the right. So let's look at what happens. On the right-hand side, these cancel, and the right-hand side just equals 3. And on the left-hand side, when I distribute it to this first term, nothing cancels. And this becomes just 2x minus 5 over x plus 5. Then when I multiply it by the second term here, now they do cancel. The x minus 5 here and the x minus 5 here cancel, and I'm left with 1 over x plus 5. Okay, so now we're making some progress. For the last step here, I'm going to multiply both sides by x plus 5. And the right side will become 3x plus 15. And on the left-hand side, all of these, when I distribute, the x plus 5s are all going to cancel. And I'm left with 2 times x minus 5 minus 1. And sure enough, excellent. Now we've ended up with a linear equation. If I distribute here on the left, this is 2x minus 10 minus 1 equals 3x plus 15. And if I subtract 3x from both sides, 2x minus 3x is minus x. This is minus 11 equals 15. Then I'll add 11 to both sides. Minus x equals 26. And multiply both sides by 1. X equals minus 26. And that's our final answer. And if you come up here and check, putting minus 26 in here makes this minus 21. It makes this part minus 31. And I don't know what it becomes if I put it in here, but it's not going to become 0. Right? If it had one of these other two factors, it would have been 0 already. So x equals minus 26 is going to be the solution to this equation. All right, so now I've got one more example to look at. This one is a little different from the other two. Here I have the square root of x plus 2 equals 4. So I want to eliminate the square root. That's kind of the nonlinear part here. And to do that, I'm going to square both sides. So on the left-hand side, the square root and the square kind of cancel each other, and I'm left with x plus 2. And on the right-hand side, 4 squared is 16. Then subtract 2 from both sides, and x equals 14. And this is another one you need to check, right? You need to make sure when working with square roots that whatever number you put in there doesn't make the expression under the square root negative. And in this case, it doesn't. If I put 4 in there, it becomes the square root of 14 plus 2. That's just the square root of 16, and there's nothing wrong with that. Okay, so that's the end of this lecture. What I kind of want you to take away here is that sometimes an equation may look complicated. It may look like it's got all kinds of messy nonlinear elements in it, but you should be aware that it pays to try manipulating it a little bit. See if you can cancel some things. See if you can get rid of some denominators, and manipulate the equation into that nice linear form that we have all these great techniques for solving.